A single beam of light reveals the hidden order of the universe through the strange physics of mirrors, reflections, and symmetry. The simple act of looking into a glass surface connects us to the fundamental laws of the physical world. When a photon of light strikes a solid surface, it does not simply bounce off like a rubber ball, but is instead absorbed and re-emitted by the electrons within the material's atoms. This process happens so quickly that it appears instantaneous to the human eye, yet it involves a complex exchange of energy at the subatomic level. The reflection we see is actually a coordinated re-radiation of light by countless trillions of electrons acting in perfect unison. Please take a moment to like and subscribe to the channel. Most objects we see every day are visible because they reflect light in every direction simultaneously, a process known as diffuse reflection. This happens because almost all natural surfaces are chemically and physically rough at the microscopic scale, scattering incoming photons into a chaotic cloud of trajectories. Even a page of a book or a wooden table consists of microscopic peaks and valleys that prevent light from maintaining a coherent image. In a true mirror, the surface is polished to such an extreme degree of smoothness that the light waves remain synchronized after they depart from the material. This specific phenomenon is called specular reflection, where the angle of the incoming light perfectly matches the angle of the departing light. Because the photons maintain their relative positions to one another, the human brain can reconstruct the original image from the bounced waves. The efficiency of a reflection depends heavily on the electrical conductivity of the material the light encounters. Metals are excellent reflectors because they possess a sea of mobile electrons that can respond and vibrate freely when hit by the electromagnetic field of a photon. This rapid vibration creates a secondary wave that cancels out the light trying to enter the metal, effectively pushing the energy back out into the room. In modern glass mirrors, a thin layer of atoms is deposited onto the back of the pane to facilitate this high-speed interaction. This metallic film is usually so thin that it would be transparent if held up to a bright light on its own. Within this microscopic layer, the laws of quantum electrodynamics dictate how every single particle of light must behave. When we look at a perfectly still lake or a polished piece of silver, we are witnessing a specific physical interaction between light and matter. This clarity is possible only because the surface is smoothed down to the scale of the light waves themselves. At this microscopic level, a mirror-like surface acts as a disciplined boundary that keeps every incoming photon in its original relative position. This orderly bounce is what scientists call specular reflection, derived from the Latin word for mirror. In specular reflection, light rays that arrive parallel to one another will depart parallel to one another. This preservation of geometry allows our eyes to perceive a clear, coherent image of the world around us. If the surface were even slightly uneven at the scale of a few hundred nanometers, this visual order would instantly collapse into a blur. The precision required for this effect is truly remarkable when we consider how small a single wave of visible light actually is. Most of the objects that fill our daily lives interact with light in a much more chaotic way. Even a surface that feels smooth to the touch, like a sheet of white paper or a painted wall, is actually a mountain range of jagged peaks when viewed through a microscope. When light hits these microscopic irregularities, the individual photons are sent flying in every possible direction simultaneously. This phenomenon is known as diffuse reflection, and it is the reason we can see objects from any angle. While you listen to these relaxing facts, it is interesting to consider why a white wall does not act like a mirror. A perfectly white wall can actually reflect over 90% of the light that hits it, which is often more than a standard household mirror. However, because that light is scattered in 1 trillion different directions, the information contained in the light waves is lost. The energy is still there, illuminating the room, but the image itself has been shattered into a soft, directionless glow. The transition from a mirror-like surface to a scattering surface is governed by a principle known as the Rayleigh criterion. This scientific rule helps physicists determine exactly how rough a surface can be before it stops acting like a mirror. According to this criterion, a surface is considered smooth if the height of its microscopic bumps is significantly smaller than the wavelength of the light hitting it. If the bumps are large enough to create a phase shift in the bouncing waves, the specular reflection begins to fail. This explains why a road might look like a dark, matte surface during a sunny day, but transforms into a shimmering mirror when it rains. The water fills in the tiny pits and valleys of the asphalt, creating a new, liquid surface that is flat enough to satisfy the Rayleigh criterion. In that moment, the scattered light of diffuse reflection is replaced by the orderly, parallel paths of specular reflection. This simple shift in surface geometry fundamentally changes how our brains interpret the physical world around us. A modern household mirror is far more than a simple piece of polished glass, acting instead as a multi-layered piece of precision engineering. At its core, the object you look into every morning is a composite structure designed to manipulate light with extreme efficiency. The majority of the mirror's thickness comes from a pane of high-quality soda-lime glass, which provides the necessary flatness and structural rigidity. However, the glass itself is not what creates the reflection, as it serves primarily as a transparent substrate and a protective shield for the delicate materials hidden behind it. The true heart of the mirror is a microscopically thin layer of metal, usually aluminum or silver, applied to the back surface of the glass. In a process known as silvering, manufacturers place the glass pane inside a specialized vacuum chamber where metallic atoms are vaporized and allowed to settle onto the surface. This creates a coating that is often only a few hundred atoms thick, yet it is dense enough to turn a transparent window into a nearly perfect reflector. This metallic film is so sensitive to the environment that it must be immediately covered by a layer of copper and several coats of protective paint to prevent the metal from tarnishing or peeling away. From the perspective of an incoming photon, the thick layer of glass is almost entirely invisible, acting as little more than a clear hallway leading to the metal. Because silica glass is chemically stable and possesses a very low absorption rate for visible light, the vast majority of photons pass through the front surface and the body of the glass without being diverted. They travel through the transparent medium until they strike the boundary where the glass meets the metal atoms. It is at this precise interface, deep inside the physical structure of the mirror, that the actual bounce occurs and the light begins its journey back toward your eyes. The science behind this metallic bond relies on the way free electrons move within the silver or aluminum layer. When the oscillating electromagnetic field of a light wave hits these electrons, they begin to vibrate at the exact same frequency as the incoming light. This vibration creates a secondary wave that radiates back out, essentially canceling the light's forward momentum and sending it back the way it came. This interaction happens so fast and so efficiently that a high-quality silvered mirror can reflect about 95% of the visible light that enters it. The glass remains a silent partner in this process, quietly shielding the silver from the moisture and oxygen in the air that would otherwise destroy the reflection within days. While the glass seems like a permanent, frozen guardian for the metal, its internal structure is actually a complex arrangement of atoms that lacks the long-range order of a crystal. This unique molecular state means that the glass might not be as eternally static as it appears to the human eye over a single lifetime. Over immense periods of time, the relationship between the solid glass and the metallic heart of the mirror begins to whisper secrets about the true nature of matter. While we perceive the mirror as a finished, unchanging object, the physics of its materials suggest a much longer story of gradual change. The way these materials hold their shape and their clarity is a testament to the stability of modern chemistry. Yet everything in the universe is subject to the slow, patient pull of deep time. Every time you look into a mirror, you are technically engaging in a form of time travel. The image staring back at you does not represent who you are in the exact present moment, but rather who you were a tiny fraction of a second ago. This happens because light, despite its incredible velocity, still requires a measurable amount of time to travel from your face to the glass and back again. This delay is an inescapable reality of physics, meaning that every reflection is a preserved memory of the immediate past. In the vacuum of empty space, light travels at a constant speed of approximately 299,792,458 meters per second. This universal speed limit is the foundation of modern physics, ensuring that information can never move instantaneously between 2 points. When light leaves the vacuum and enters a denser material like the glass of a mirror, it encounters the electromagnetic fields of trillions of atoms. These interactions cause the light to slow down significantly, changing the timing of the reflection in a way that is subtle but scientifically profound. The degree to which light slows down in a material is determined by its refractive index, which is a ratio of its speed in a vacuum compared to its speed in that specific substance. For typical silica glass used in most household mirrors, the refractive index is approximately 1.5. This value indicates that light travels about 33% slower through the glass than it does through the air or a vacuum. As a photon enters the front surface of the mirror, it begins a slower, more deliberate journey toward the metallic backing before it can be reflected. Imagine you are standing exactly 1 meter away from a large mirror in a quiet, dimly lit room. To see your own eyes, light must travel 1 meter to hit the mirror, and then another meter to return to your pupils, covering a total distance of 2 meters. Even at the staggering speed of light, this journey takes about 6.7 nanoseconds to complete. While a nanosecond is only 1/1000th of a second, it represents a physical gap between the person standing in the room and the image held within the glass. This infinitesimal delay means that if you were to blink, your reflection would technically blink a few nanoseconds after you do. The human brain is not wired to perceive such tiny windows of time, so the reflection appears perfectly synchronized with your movements. Yet, the physics of the universe dictates that the person you see in the mirror is always younger than the person looking into it. This temporal lag is a constant companion in our daily lives, a silent reminder that we are always observing the history of the world around us. The thickness of the glass adds its own small contribution to this delay because of how the refractive index dictates the passage of photons. As light moves through the silica structure, it is constantly absorbed and re-emitted by electrons, a process that creates the macroscopic effect of slowing down. This means the thicker the mirror glass is, the further back into the past you are peering when you check your reflection. Every millimeter of transparent material acts as a tiny bridge across time, stretching the moment just a little bit further. Scientists use these precise measurements of light speed and delay to calibrate advanced optical equipment and deep space telescopes. In the world of high-precision physics, the nanoseconds lost during a reflection are critical data points that must be accounted for to ensure accuracy. Even in the comfort of your home, the mirror functions as a sophisticated instrument that captures and returns light according to these rigid laws. It is a quiet, silvered window that shows us a world that has already happened, even if that history is only a few billionths of a second old. In a theoretical sense, a perfect mirror that reflects every single wavelength of visible light with equal intensity would be categorized as white. According to optical physics, the color white is defined by the presence of all visible frequencies being sent back to the observer in a balanced manner. While most people describe a mirror as being silver or metallic, an ideal reflective surface has no inherent color of its own, because it does not prioritize one part of the spectrum over another. If you were to look at a mathematically perfect mirror, its baseline identity would be pure, unadulterated white. The reality of our physical world is slightly more complex. Most mirrors found in modern homes and offices actually possess a subtle but measurable green hue that only reveals itself under specific conditions. This occurs because the silica glass used to protect the reflective silver or aluminum backing is not perfectly transparent across all wavelengths. While the material appears clear to the casual observer, the atomic structure of soda-lime glass absorbs a tiny fraction of energy from the red and blue ends of the spectrum. This physical interaction leaves the green light slightly more prominent in the reflection, defining the mirror's true physical color. This subtle shift is usually invisible to the naked eye. When two mirrors are placed directly across from each other, they create an infinite corridor of reflections that gradually reveals the green tint of the glass. This phenomenon, often called a mirror tunnel, occurs as light bounces back and forth between the two surfaces dozens or even hundreds of times. With every single bounce, a small amount of red and blue light is filtered out by the glass while the green light persists. As the light travels deeper into the reflected distance, the images become darker and take on a noticeably emerald tone. It is a visual record of the exhaustion of light. Even the highest quality household mirrors only reflect about 85 to 95% of the photons that strike their surface. The remaining energy is absorbed by the silica and the metallic backing, slowly converting the light into minute amounts of thermal energy. In a mirror tunnel, you are essentially watching light lose its momentum in real time as it struggles to maintain its intensity through multiple layers of glass. By the time you view the 50th or 60th reflection, the light has passed through so much material that the dominant green wavelength is the only part of the spectrum remaining. Science provides a precise name for this specific behavior. Researchers using a device called a spectrophotometer have confirmed that common mirrors reflect light most efficiently at a wavelength of about 510 nanometers. This specific measurement falls squarely within the green portion of the visible light spectrum, providing empirical evidence for the mirror's hidden color. According to studies published in the American Journal of Physics, this green peak is a fundamental characteristic of standard soda-lime glass. Understanding this optical signature allows engineers to create specialized low-iron glass for scientific mirrors that appear much more neutral. A common misconception persists that a mirror possesses the unique ability to flip an image from left to right. When you stand before your reflection and raise your right hand, the figure in the glass appears to raise their left hand. This leads the human brain to conclude that the mirror has somehow performed a horizontal transformation on the light. However, the physical reality is that a mirror does not flip things horizontally at all, but rather performs a transformation along a completely different axis. This concept is one of the most misunderstood principles in basic optics. The light rays reflecting off your body travel in straight, parallel lines directly toward the surface of the glass and bounce straight back. Your right hand remains on the right side of the mirror's surface, and your left hand remains on the left. If a mirror truly flipped images left to right, your head would also be where your feet are, as there is no physical reason for a mirror to prioritize the horizontal over the vertical. Consider a simple, quiet experiment to illustrate this. Imagine you are holding a clear piece of plastic with the word "light" written on it in bold, black ink. If you hold this transparent sheet up to a mirror, you will notice that the word still reads perfectly from left to right in the reflection. This happens because you have not turned the object around to face the mirror. The light is passing through the plastic and reflecting back exactly as it is oriented. It is only when we use opaque objects that the illusion of flipping begins. When you hold a standard piece of paper with writing on it, you must physically turn the paper around so the ink faces the glass. It is your own hand that performs the flip, rotating the paper 180 degrees to make it visible to the reflective surface. The mirror is simply showing you what is currently facing it, without adding any rotational movement of its own. These relaxing facts help us peel away the layers of how we perceive the world. As you listen to these descriptions and begin to fall asleep, the mind can let go of these optical puzzles and simply accept the steady behavior of light. The mirror is essentially a passive participant in the room, acting as a silent recorder of the photons that happen to strike it. It does not possess the mechanical or mathematical means to decide which way a shape should point. To understand this more clearly, imagine you are wearing a glove on your right hand. If you were to walk into the mirror and stand where your reflection is, you would find that the glove would no longer fit your right hand correctly. This is because the mirror has performed a front-to-back reversal rather than a side-to-side one. This is known in physics as a reversal of the version, or the z-axis, which is the direction pointing directly into and out of the mirror. The mirror acts like a printing press or a rubber stamp. When a stamp is pressed onto a page, the image is not rotated. It is simply pressed forward. The part of the stamp that was closest to the paper becomes the part of the image that is deepest on the page. In the same way, the mirror reflects the tip of your nose because it is the closest point to the glass, making it appear in the foreground of the reflection. Scientific studies in cognitive psychology, such as those found in the journal Perception, suggest our brains struggle with this because we subconsciously map our own body onto the reflection. We imagine ourselves walking around to the other side of the glass and turning around to face forward. Because we always turn horizontally when we face someone, we assume the mirror has done the same thing. The truth is that the mirror is a perfect map of depth. Every point on your body is reflected at an equal distance behind the glass as it is in front of it. Your right ear is reflected directly across from your right ear, and your left shoulder is reflected directly across from your left shoulder. There is no crossing of paths and no switching of sides in the journey of the photons. It is a remarkably consistent and simple process. By removing the human element of interpretation, we see the mirror for what it truly is, a depth inverter. It takes the world and turns it inside out along the line of sight. This constant, unwavering geometry is what makes reflections so predictable and reliable for everything from grooming to advanced scientific measurements. Light interacting with a polished surface creates a doorway into a geometric realm governed by the fundamental laws of mirrors. It is a world of precision. The moment a photon strikes a metallic surface, it is absorbed and immediately re-emitted by the electrons in the metal. This process, known as specular reflection, happens with such consistency that the angle at which the light hits the surface is exactly equal to the angle at which it bounces away. On a microscopic level, most surfaces are jagged and uneven, causing light to scatter in every direction. This is called diffuse reflection, which is why a white sheet of paper reflects light but does not show your face. Please like and subscribe if you enjoy learning. For a surface to act as a mirror, its imperfections must be smaller than the wavelength of the light hitting it. This is the Rayleigh criterion, and it explains why a rough piece of wood cannot produce a clear reflection while polished silver can. Modern mirrors are usually made by applying a thin layer of aluminum or silver to a sheet of glass in a vacuum. This metallic coating is the actual reflective agent, while the glass serves only to protect the metal from oxidation and physical damage. When you look into a mirror, you are technically looking into the past by a few billionths of a second. This is because light travels at a finite speed of roughly 300,000 kilometers per second, and it must travel from your face to the glass and back to your eyes. The refractive index of silica glass is about 1.5, which means light slows down significantly as it passes through the clear layer before hitting the metal. This change in speed causes the light to bend slightly, a phenomenon that engineers must account for when designing high-precision optical instruments. While we often think of mirrors as colorless, a standard household mirror actually has a very slight green tint. This is because the atoms in the glass absorb a tiny amount of light in the red and blue spectrums, while reflecting green light more efficiently. This green hue becomes obvious when two mirrors face each other, creating an infinite tunnel of reflections. With each bounce, more red and blue light is absorbed, leaving only a deep, mossy green visible in the distant depths of the tunnel. Common wisdom suggests that mirrors flip images from left to right, but this is a scientific misconception. If you point to the right, your reflection also points to the right, showing that the horizontal axis remains perfectly intact. The true transformation is a front-to-back reversal along the z-axis, which points directly into the mirror. Imagine a glove being turned inside out. This is the same mathematical operation a mirror performs on the light rays it receives. Your brain interprets these reflected rays as though they traveled in a straight line from behind the wall. This creates a virtual image, a perception of an object in a space where no light actually exists. How do the individual rays of light stay organized enough to form a coherent picture after a collision? Concave mirrors are curved inward like a bowl, causing parallel rays of light to converge at a single focal point. This property is used in reflecting telescopes to gather the faint light of distant stars and concentrate it into a sharp image. In contrast, convex mirrors curve outward, scattering light rays and widening the field of view. These are commonly used as safety mirrors in parking garages, because they allow you to see around corners that would otherwise be hidden. The focal length of a curved mirror is exactly half of its radius of curvature. This geometric rule allows scientists to calculate exactly where an image will appear based on how steeply the glass is ground. Every time light reflects off a surface, it loses a tiny amount of its energy to the material as heat. Even the most perfect laboratory mirrors can only reflect about 99.9% of the light, meaning an infinite number of reflections would eventually result in total darkness. Conservation of energy dictates that the photons not reflected must be absorbed by the atoms of the mirror. According to the textbook OpenStax Physics, this energy increases the thermal vibration of the molecules, slightly warming the glass with every glance. When light travels through water and hits the boundary of the air at a shallow angle, it may not pass through at all. Instead, it reflects back into the water perfectly, a phenomenon known as total internal reflection. This critical angle is the reason why, when looking up from the bottom of a swimming pool, the surface of the water can look like a shimmering silver mirror. It is a natural result of the difference in optical density between two transparent substances. Total internal reflection is the foundational principle behind fiber optic cables. By trapping light inside a thin strand of glass, We can send data across oceans at nearly the speed of light, with the photons bouncing off the walls of the cable without ever escaping. The glass used in fiber optics is so incredibly pure that if the ocean were made of it, you could see the floor of the Mariana Trench from the surface. This clarity ensures that the signal does not fade away during its journey through the Earth's digital nervous system. Atmospheric layers can also act as mirrors when there are sharp differences in air temperature. A mirage on a hot highway is actually a reflection of the sky, created because the hot air near the pavement is less dense than the cooler air above it. This bending of light makes the road appear wet, but what you are seeing is a displaced image of the atmosphere. These relaxing facts help us understand how our senses can be fooled by the simple physics of heat and light. A more complex version of this is the Fata Morgana, a superior mirage that makes ships appear to float upside down in the sky. This happens when a layer of warm air sits on top of cold air, bending light rays downward toward the curvature of the Earth. During the Apollo missions, astronauts placed small mirrors called retroreflectors on the surface of the Moon. These devices are made of corner cube prisms that always reflect light directly back to its source, regardless of the angle at which it arrives. Earth-based observatories fire high-powered lasers at these lunar mirrors to measure the distance to the Moon. By timing how long it takes for the light to return, scientists can track the Moon's orbit with a precision of just a few millimeters. Night-roaming animals like cats and owls have a biological mirror behind their retinas called the tapetum lucidum. This reflective layer gives the eye's photoreceptors a second chance to catch photons that were missed the first time. This adaptation is why animal eyes appear to glow in the dark when caught in a beam of light. It significantly improves their vision in low-light conditions, allowing them to navigate the world using only the faint reflection of the stars. Does the reflection of a sound wave behave with the same geometric certainty as the reflection of a light wave? Sound waves reflect off hard surfaces to create echoes, but the human brain can only distinguish an echo if it arrives more than 1/10 of a second after the original sound. This requires the reflecting surface to be at least 17 meters away from the source. In a whispering gallery, such as the dome of St. Paul's Cathedral, the circular walls allow sound to reflect repeatedly along the perimeter. This focuses the sound waves so efficiently that a whisper can be heard clearly on the opposite side of the massive room. Beyond the physical world of glass and light, the universe itself is built on the foundation of symmetry. In 1915, mathematician Emmy Noether proved that every symmetry in nature corresponds to a fundamental law of conservation. Spatial translation symmetry means that the laws of physics are the same here as they are on the other side of the galaxy. This symmetry, is the direct reason why momentum is conserved throughout the entire universe. Similarly, rotational symmetry implies that physics does not change if you turn in a circle. This balance is what ensures the conservation of angular momentum, keeping planets in their orbits and galaxies in their slow, majestic spins. Equations in physics often exhibit time reversal symmetry, meaning they work perfectly whether time flows forward or backward. At the level of individual atoms, a video of particles colliding would look exactly the same if it were played in reverse. While microscopic physics is symmetrical, the macroscopic world is not, due to the law of entropy. This creates a one-way arrow of time, even though the fundamental building blocks of the universe do not seem to care about direction. Science for sleep often explores how these deep patterns define our reality. One of the most startling discoveries in modern physics is that the universe is not a perfect mirror of itself. In the 1950s, the Wu experiment showed that certain subatomic interactions have a preferred handedness. This breaking of parity symmetry proved that the laws of nature can actually distinguish between left and right in the weak nuclear force. Antimatter can be thought of as a cosmic reflection of ordinary matter. Every particle of antimatter has the same mass as its counterpart, but possesses the opposite electrical charge, like a proton and its mirror image antiproton. When a particle of matter meets its antimatter reflection, they annihilate one another instantly. This process converts all of their mass into pure energy, representing the most efficient possible conversion of matter according to Einstein's famous equation. The James Webb Space Telescope uses 18 hexagonal mirrors made of beryllium to peer into the deepest reaches of space. Beryllium is used because it is incredibly light and maintains its shape even at the frigid temperatures of deep space. Each of these mirrors is coated in a layer of gold that is only a few hundred atoms thick. Gold is the perfect choice for an infrared telescope because it reflects 99% of infrared light, allowing the telescope to see the heat of the very first stars. Some specialized telescopes use liquid mercury instead of glass to create a perfect reflecting surface. By spinning a pool of mercury at a constant speed, centrifugal force naturally pushes the liquid into a perfect parabolic shape. This liquid mirror is significantly cheaper than a glass one of the same size, though it can only point straight up at the zenith. It is a beautiful example of how gravity and motion can work together to create optical perfection. If you have ever seen a one-way mirror in an interrogation room, you have witnessed a clever trick of lighting rather than a special type of glass. These are actually half-silvered mirrors that reflect half the light and allow the other half to pass through. The mirror effect only works if one room is brilliantly lit and the other is kept in total darkness. People in the bright room see their own reflection because it overpowers the tiny amount of light coming from the dark side. Why is it that at the quantum level, an atom can bounce off a surface without ever physically touching it? This phenomenon is called quantum reflection, and it occurs when the wave-like nature of a slow-moving atom interacts with the attractive force of a solid surface. Instead of sticking to the surface, the atom's wave function is reflected back into space. In the vacuum of empty space, two mirrors placed very close together will experience a physical force pushing them together. This is the Casimir effect, caused by the fact that the tiny gap between the mirrors limits the types of quantum fluctuations that can exist there. The pressure from the fluctuations outside the mirrors is greater than the pressure between them. This measurable force proves that even empty space is teeming with virtual particles and energy. Massive objects in space, like clusters of galaxies, can act as gravitational mirrors. According to general relativity, gravity bends the fabric of space-time, which in turn bends the path of light. This can create multiple images of the same distant galaxy, appearing as a ring or a series of arcs in the sky. These gravitational lenses allow astronomers to see objects that would otherwise be far too distant and faint to detect. Reflective surfaces are also essential for managing heat in the vacuum of space. Spacecraft are often wrapped in multi-layer insulation that looks like gold or silver foil, which reflects the sun's intense radiant heat. This material, often made of aluminized mylar, reflects infrared radiation just as a bathroom mirror reflects visible light. It prevents the delicate electronics inside a satellite from being cooked by the unfiltered sun. Planets also have a measurable reflectivity known as albedo. The Earth's albedo is roughly 30%, meaning nearly a third of the sunlight that hits our planet is reflected back into space by clouds, ice, and snow. Fresh snow has one of the highest albedos on Earth, reflecting up to 90% of the sun's rays. This natural mirror effect is a critical component of the global climate system, as it helps keep the polar regions cold. How does the human brain distinguish between a real object and its reflection? In neuroscience, the mirror self-recognition test is used to measure self-awareness in different species. Humans usually pass this test around the age of 18 months, realizing that the smudge of paint they see in the mirror is on their own forehead. The primate brain contains a special class of cells known as mirror neurons. These neurons fire both when an individual performs an action and when they watch another individual perform that same action. These cells are thought to be foundational for learning through imitation and understanding the intentions of others. They allow us to mentally mirror the experiences of those around us, creating a bridge between different minds. Contrary to a popular myth, the glass in ancient cathedral windows is not thicker at the bottom because it flowed downward over time. Glass is an amorphous solid, and while its atoms are disordered, it would take billions of years for it to flow even a fraction of a millimeter. The variation in thickness is actually a result of the way glass was manufactured centuries ago. The windows were often installed with the thicker edge at the bottom for stability, not because the material was slowly melting. If a mirror were left in a perfectly stable and inert environment, it could potentially last for millions of years. However, over vast stretches of time, the silver or aluminum layer would eventually succumb to atomic diffusion, slowly losing its reflective power. The universe is a place of balance, where every action has an equal and opposite reaction. This symmetry is the quiet engine that keeps the stars burning and the planets turning in their predictable paths. Through the study of reflections, we have learned to see the invisible, from the microscopic structures of cells to the furthest edges of the observable cosmos. Each bounce of a photon is a piece of data that helps us map the reality of the physical world. Learning about the mechanics of light provides a sense of peace, as it reveals a universe that is deeply organized and logical. These bedtime listening experiences are a way to appreciate the silent beauty of the laws that govern our lives. As you consider the vastness of these concepts, remember that every reflection you see is a testament to the constancy of physics. The world behind the glass is a perfect mathematical shadow of our own, following rules that never change. I hope these relaxing facts have brought you a sense of wonder and calm. Please subscribe to the channel if you would like to join us for more scientific explorations. The quiet logic of light continues to shine in the dark, reflecting the enduring mystery of the world around us. A mirror does not have to be flat to provide a clear and useful reflection of the physical world. When a reflective surface is curved, it gains the ability to manipulate the path of light rays in predictable and mathematically precise ways. This curvature changes how the law of reflection applies across the entire surface of the material. By shaping the glass into a specific arc, engineers can control whether an image appears larger, smaller, or even upside down. A concave mirror is curved inward like the interior of a bowl, which causes it to function as a highly efficient light collector. When parallel rays of light strike this inward curving surface, they are reflected toward a central axis. This process is known as convergence, and it allows the mirror to concentrate energy from a large area into a very small, intense space. Shaving mirrors and makeup mirrors use this specific curvature to provide a magnified view of a person's face. If every individual photon is simply bouncing off a tiny point on the glass, how do these millions of independent light rays know exactly where to converge to create a perfect image? The answer lies in the geometry of the curve itself, which ensures that every ray of light follows the path of least time to reach a specific destination. For a spherical concave mirror, this destination is a unique spot in front of the glass called the focal point. At this exact coordinate, the reflected rays cross over one another, creating a concentrated point of light and heat. If you place an object further away than this point, the image will actually appear inverted to your eyes. The distance between the center of the mirror and this convergent spot is known as the focal length. This measurement is a fundamental property of the mirror's geometry and is determined by the radius of the sphere from which the mirror was cut. In a simple spherical mirror, the focal length is exactly half of the radius of curvature. This geometric rule allows scientists to calculate exactly where an image will form before the mirror is even manufactured. In contrast to the inward curve, a convex mirror bulges outward toward the light source like the back of a spoon. Instead of bringing light rays together, this shape causes them to spread out or diverge as they bounce away. Because the rays are scattering in many directions, the brain perceives the image as coming from a virtual point behind the mirror. This creates a wide-angle view that captures much more of the surrounding environment than a flat surface ever could. This ability to compress a vast field of vision into a small space makes convex mirrors essential for safety in the physical world. They are commonly placed in the corners of parking garages or at the ends of narrow hallways to help people see around blind spots. Because the reflected rays are diverging, the objects in the mirror appear smaller and further away than they truly are. This distortion is a necessary trade-off for the increased situational awareness the wide-angle reflection provides. While spherical curves are common, a parabolic shape is required to bring light into a truly perfect, sharp focus without any blurring. Spherical mirrors often suffer from a slight distortion called spherical aberration, where rays hitting the edges of the mirror focus at a different spot than those hitting the center. A parabola corrects this by ensuring every single ray meets at the exact same point, regardless of where it strikes. This precision is why the massive mirrors in professional astronomical telescopes are ground into a parabolic shape. When two mirrors are placed perfectly parallel to one another, they create a visual phenomenon that appears to stretch into infinity. This alignment allows a single photon of light to bounce back and forth between the two reflective surfaces in a continuous loop. While the human eye perceives an endless hallway of reflections, the laws of physics dictate that this journey must eventually come to an end. Even the highest quality mirrors available today are unable to reflect 100% of the light that strikes them. Every time a photon hits the surface of a mirror, a tiny fraction of its energy is lost to the material itself. In a standard household mirror, approximately 4 to 10% of the light is absorbed during every single bounce. This means that after only a few dozen reflections, the original image has lost most of its clarity and brightness. Even with specialized dielectric mirrors used in laboratory settings, which can reflect over 99% of light, the sequence of bounces is still finite. The light that is not reflected does not simply vanish into nothingness, as energy must always be conserved within a closed system. Instead, the energy from the absorbed photons is transferred to the atoms that make up the mirror's coating and glass substrate. As the photons strike the metallic layer, they give up their electromagnetic energy, which then manifests as microscopic vibrations within the solid material. This process is known as thermal agitation, where the kinetic energy of the atoms increases, slightly raising the temperature of the mirror. According to the fundamental principles outlined in open stacks physics, this conversion from light energy to thermal energy is a prime example of the first law of thermodynamics. The mirror acts as a transducer, changing the form of the energy rather than destroying it. Because of this constant drain on the light's intensity, a photon in a typical mirror tunnel will usually survive for fewer than 100 bounces before it is completely converted into heat. This rapid absorption explains why the deeper reflections in a mirror tunnel always appear darker and less distinct than the ones in the foreground. Have you ever wondered how the slight imperfections in a flat surface can change the path of a beam of light over a long distance? The precision required to keep light bouncing perfectly straight is nearly impossible to achieve outside of a vacuum. Even a microscopic tilt in one of the mirrors will cause the light to eventually veer off the edge of the reflective surface and escape. In a perfectly aligned system, the light would still eventually fade because the glass itself acts as a barrier. Every time the light passes through the thickness of the glass to reach the silver backing, the silica molecules scatter a small portion of the wave. This scattering effect is cumulative, adding another layer of energy loss to the absorption occurring at the metallic interface. Over many iterations, the light waves lose their coherence, and the reflected image becomes a blurry, green-tinted shadow of the original object. This green hue is a physical signature of the glass, representing the specific wavelengths of light that the material is most efficient at transmitting. The energy that doesn't make it through simply adds to the quiet, invisible warmth of the mirror's surface. The transition from a solid mirror to the reflective properties of a liquid depends entirely on the concept of optical density. Every material through which light travels possesses a specific refractive index, which determines how much the speed of light slows down as it enters that medium. When a light ray attempts to move from a dense medium like water into a less dense medium like air, it experiences a physical shift in its trajectory. This bending occurs at the exact boundary where the two substances meet, a phenomenon that governs how we perceive the world from beneath the surface. As the angle at which the light hits this boundary becomes shallower, the bending becomes more pronounced. Eventually, a specific threshold is reached where the light can no longer escape into the air at all. This threshold is known in physics as the critical angle, a precise geometric limit defined by the relationship between the two different materials. At any point beyond this angle, the boundary between the water and the air ceases to be a window and transforms into a flawless, silvered mirror. This phenomenon is governed by the principles of Snell's law, which describes the predictable relationship between the angles of incidence and refraction. Conceptually, this law explains that light always seeks the path that takes the least amount of time to travel between 2 points. When light moving through water hits the air at a very steep angle, it must bend away from an imaginary line perpendicular to the surface. As that angle grows wider, the light is forced to bend so far that it is eventually reflected back down into the water. This process is called total internal reflection, because 100% of the light energy is retained within the original medium. Unlike a glass mirror, which always absorbs a tiny fraction of light as heat, total internal reflection is theoretically perfect. It allows for a level of brightness and clarity that artificial mirrors struggle to replicate. This is why the underside of a calm water surface can appear more vivid and reflective than a polished sheet of silver. Imagine a scuba diver drifting slowly at the bottom of a clear, quiet lake during the late afternoon. As they look directly upward, they see a circular window of light where the sky and the trees along the shore are visible. This circular opening is often called Snell's window, and it represents the only area where light from the outside world can penetrate the water's surface to reach the diver's eyes. Outside of this central circle, the water above does not look like water or sky at all. Instead, the rest of the surface stretching out toward the horizon looks like a vast, shimmering sheet of liquid mercury. The diver can see the rocks on the lake floor and the slow movement of fish reflected perfectly in the ceiling of the water. Because of total internal reflection, the boundary between the lake and the atmosphere has become a solid-looking barrier of light. Every ripple on the surface creates a distorted, beautiful dance of reflections that mimic the world below rather than the world above. The transition across the critical angle is instantaneous and absolute, creating a sharp divide in the diver's field of vision. This optical boundary is so reliable that it is used as a fundamental tool in high-precision engineering and telecommunications. In the quiet darkness of the lake, this mirror is a natural byproduct of how light interacts with the density of the environment. The diver remains suspended in a world where the ceiling is a reflection of the floor, creating a sense of infinite, quiet space. Modern technology harnesses this natural phenomenon of total internal reflection to move information across the planet at the speed of light. While a diver sees this effect on the surface of a lake, engineers replicate it inside incredibly thin strands of glass known as fiber optics. These strands are often no thicker than a human hair, yet they act as a perfect mirror-lined hallway for photons. By carefully controlling the angle at which light enters the fiber, the photons are forced to bounce off the internal walls repeatedly without ever escaping. Each time a photon hits the boundary between the inner core of the glass and its outer cladding, it experiences total internal reflection. This allows the light to travel around corners and across thousands of miles of undersea cables while maintaining its intensity. Because the reflection is nearly perfect, very little signal is lost to the surroundings during the journey. This constant, rhythmic bouncing creates a silent stream of data that powers the modern digital world. The glass used in these fibers is manufactured to a level of purity that is difficult to find anywhere else in nature. In a standard window pane, light begins to dim after traveling through just a few inches of material due to microscopic impurities. However, fiber optic glass is so incredibly clear that if the entire Earth's ocean were made of it, you could stand on the surface and see the bottom of the Mariana Trench with perfect clarity. This extreme transparency ensures that the light can travel for miles before needing a boost from an electronic amplifier. Even at this high level of purity, the glass remains an amorphous solid that guides the light with unwavering precision. Scientists at Bell Labs and other institutions have spent decades refining the chemical composition of these fibers to minimize any scattering of the light particles. Every millimeter of the strand is a testament to the physics of reflection working in a confined, controlled space. Inside the dark heart of a fiber optic cable, the light exists in a state of perpetual redirection, trapped by the laws of optics. The quiet pulse of these light waves forms the backbone of global communication, moving silently beneath our feet and across the floors of the deep sea. The same principles of reflection that guide light through glass also apply to the vast, invisible layers of the atmosphere surrounding our planet. Light does not always travel in a perfectly straight line when it encounters varying temperatures in the air. When the sun warms the ground, it creates a thin layer of hot air just above the surface, while the air higher up remains significantly cooler. This temperature difference causes a change in the air's density, which in turn changes its refractive index. As light travels downward toward the hot ground, it begins to bend more and more sharply. As the light moves from the solid world of glass into the invisible layers of the air, it begins to behave in ways that seem almost magical. The atmosphere is not a uniform block of gas, but a shifting collection of layers with different temperatures and densities. These variations act like a series of invisible lenses and mirrors that can bend or reflect light rays before they ever reach the human eye. Under the right conditions, a simple patch of air can mimic the reflective properties of a polished silver surface. Temperature gradients play a fundamental role in how the atmosphere manipulates the path of a photon. When the sun beats down on a flat surface, such as a long stretch of highway or a vast desert floor, the ground absorbs an immense amount of thermal energy. This heat is then transferred to the very thin layer of air sitting directly above the surface, making it much hotter than the air just a few feet higher. Because hot air is less dense than cold air, it has a lower refractive index, meaning light travels through it at a slightly different speed. This change in density creates a boundary that forces light to curve instead of traveling in a straight line. As light from the sky moves downward toward the hot ground, it enters the warmer, less dense layer and begins to refract. If the angle is shallow enough, the light does not hit the ground at all, but instead curves back upward toward the observer. This phenomenon is known in physics as a gradient of refraction, and it effectively turns a layer of air into a giant, shimmering mirror. The result of this atmospheric bending is the common inferior mirage, which many people recognize as the appearance of water on a dry road. What the observer is actually seeing is a reflection of the blue sky or distant clouds appearing on the ground. The brain is accustomed to seeing light travel in straight lines, so it interprets the reflected sky as a pool of liquid sitting on the surface. This creates a convincing illusion of a shimmering lake that seems to disappear as one gets closer to the source of the reflection. The physics of an inferior mirage are governed by the same principles of total internal reflection found in high-end optics. Because the light is reflecting off a lower, hotter layer of air, the image appears inferior, or below the real object being reflected. This specific type of mirage is a constant reminder that the air itself can serve as a medium for reflection, just as effectively as a pool of still water. These calming scientific concepts make for excellent bedtime listening, as the mind begins to settle into a state of quiet observation. Beyond the simple illusion of water, these atmospheric mirrors can distort the shapes of distant objects like mountains or buildings. When the light rays are bent upward by the heat, the base of a distant object might seem to vanish or blend into the reflected sky. This creates the impression that the object is floating slightly above the horizon, a visual trick caused entirely by the way heat changes the density of the air. The atmosphere acts as a dynamic, ever-changing optical instrument that constantly redirects the flow of light around us. The Fata Morgana is a complex and rare form of superior mirage that transforms the horizon into a shifting gallery of towering castles and distorted cliffs. Unlike the common puddles seen on hot asphalt, this phenomenon occurs when a layer of warm air sits directly on top of a much colder layer of air. This specific arrangement is known in meteorology as a temperature inversion, where the standard rule of cooling air is reversed. When light from a distant object enters this layered atmosphere, it does not travel in a straight line, but instead follows a graceful, downward curve. This bending of light is so precise that it can channel images from far beyond the natural curve of the Earth, bringing hidden vistas into clear view. The physics behind this celestial mirror relies on the varying density of the air layers. Cold air is significantly denser than warm air, and as light passes between these different densities, it refracts at a sharp angle. In a fata morgana, the light rays are bent downward toward the observer by the warmer air above, creating an image that appears much higher than the actual object. The result is a superior mirage, where the reflected world seems to float serenely in the sky. Because the atmosphere is rarely perfectly still, these images often flicker or stretch, transforming simple rocks or waves into majestic, vibrating structures that seem to defy gravity. History is filled with accounts of sailors who were mesmerized by the sight of phantom ships drifting through the clouds. One of the most famous examples of this involves the Flying Dutchman legend, which many scientists believe was inspired by the Fata Morgana. On the cold waters of the North Atlantic or the Baltic Sea, the temperature inversion can become so stable that it creates a near-perfect reflection of a distant vessel. To an observer on another ship, the refracted light creates a duplicate image of the boat appearing directly above the real one. In many documented cases, the physics of the air layers actually flips the image vertically, making it appear as if a massive ship is sailing upside down across the heavens. These historical sightings were often interpreted as omens, but they are actually beautiful demonstrations of atmospheric optics. The way the light bends depends entirely on the steepness of the temperature gradient between the cold sea and the air. If the transition is smooth, the image remains clear and steady. If the air is turbulent, the reflected ship may appear to grow tall or compressed like an accordion. This stretching effect is what gives the Fata Morgana its name, referring to the Arthurian sorceress Morgan Le Fay, who was said to create illusory palaces over the sea to lead travelers astray. The ocean provides the perfect laboratory for these relaxing facts to manifest. Because water retains its temperature much longer than the air does, the surface of a cold sea can chill the lowest level of the atmosphere while the sun warms the air higher up. This creates a long, invisible lens that can span dozens of miles across the open water. When you look out at a calm, cold horizon, you are essentially looking through a giant, natural prism that is constantly adjusting itself. The light waves move slowly through these layers, curving and folding in a silent dance that brings the distant world into soft, ethereal focus. Watching a Fata Morgana develop is a lesson in the patience of the natural world. The images do not snap into place, but rather drift into existence as the air layers settle into their specific densities. A distant low-lying island might slowly grow into a series of jagged peaks, or a simple boat might appear to have multiple hulls stacked on top of one another. These vertical distortions are a hallmark of the superior mirage, showing us that the atmosphere is not a transparent void, but a physical substance capable of bending the very fabric of what we see. As the light continues its quiet journey toward the eye, it carries with it the distorted but beautiful truth of a world reflected by the air itself. The journey of a photon does not always end at the edge of our atmosphere, as some of the most precise reflections in the known universe occur 250,000 miles away on the lunar surface. To understand how we measure the heavens, we must look at the small, suitcase-sized arrays left behind by the Apollo astronauts during their historic walks on the moon. These devices are not typical flat mirrors like the ones found in a bathroom, but are instead sophisticated arrays of hundreds of small fused silica prisms. These prisms are specifically designed to be retroreflectors, which are optical devices that possess the unique ability to reflect light directly back to its source regardless of the angle at which the light hits them. While a standard mirror reflects light at an angle equal to its arrival, a retroreflector uses a specific geometric shape known as a corner cube to ensure the light returns home. A corner cube consists of 3 mutually perpendicular reflecting surfaces, much like the inner corner of a cardboard box where the floor and 2 walls meet. When a beam of light enters this corner, it bounces off all 3 surfaces in quick succession and emerges traveling in a path exactly parallel to its entry point. This geometric certainty allows scientists on Earth to aim a signal at the moon and be absolutely confident that the reflection will find its way back to the exact telescope that sent it. The most famous of these installations is the Lunar Laser Ranging Retroreflector Array, which was placed on the moon by the Apollo 11 crew in July of 1969. Since that moment, this passive piece of equipment has sat silently in the lunar dust, requiring no power source and no maintenance to continue its scientific mission. 2 subsequent Apollo missions, 14 and 15, also deployed similar arrays to create a wide network of reflective points across the lunar landscape. By having multiple points of reflection, researchers can account for the slight wobbles in the moon's rotation and orientation as it orbits our planet. To make use of these distant mirrors, specialized observatories on Earth fire incredibly powerful, short-pulsed lasers through large telescopes aimed at the specific coordinates of the landing sites. Each laser pulse contains billions of photons, yet the journey is so long and the target so small that only a tiny fraction of that light actually hits the retroreflector. Of the massive amount of light sent toward the moon, often only a single photon survives the round trip to be detected by the sensitive equipment back on Earth. This lonely photon carries with it a wealth of data about the scale of our solar system and the nature of gravity itself. The primary goal of this constant laser firing is to measure the round-trip time of the light, which takes approximately 2.5 seconds to travel to the moon and back. By multiplying this time by the speed of light, Scientists can calculate the distance between the Earth and the Moon with a precision that is almost difficult to comprehend. Current measurements are accurate to within a few millimeters, allowing us to see the Moon's orbit with the clarity of a high-resolution map. This level of precision has revealed that the Moon is not staying in a fixed orbit, but is actually spiraling away from the Earth at a rate of about 3.8 centimeters per year. Beyond tracking the Moon's slow departure, these reflections provide a rigorous test for the fundamental laws of physics. By monitoring the lunar orbit so closely, researchers can check for any tiny deviations that might suggest a flaw in Einstein's theory of general relativity. The Moon essentially acts as a giant laboratory weight, hanging in the vacuum of space and responding to the gravitational pull of the Earth and the Sun. These relaxing facts remind us that even the most distant objects in our sky are connected to us by the simple, unwavering behavior of reflected light. The laser beams continue to pulse through the night, bridging the gap between worlds and turning the Moon into a mirror for our own scientific curiosity. Nature has its own way of engineering mirrors, often placing them inside the living tissues of creatures that navigate the deepest shadows of the night. This biological adaptation is a masterclass in biophysics, where the anatomy of an eye is modified to squeeze every possible bit of information out of a dim environment. At the heart of this ability is a specialized reflective layer known as the tapetum lucidum, a term that translates from Latin as bright tapestry. This structure is not located on the surface of the eye, but is tucked away deep inside, sitting directly behind the retina. In the quiet hours of the night, this hidden mirror acts as a light-intensive system for animals that need to see when the sun has long since disappeared. The retina itself is the part of the eye that contains photoreceptors, which are the cells responsible for converting light into electrical signals for the brain. In a standard eye without this reflective layer, any photon of light that misses a photoreceptor on its first pass is simply absorbed by the dark tissue behind it and lost forever. However, the presence of the tapetum lucidum changes this fundamental interaction by providing a second chance for detection. When a photon enters the eye of a nocturnal animal and passes through the retina without being caught, it strikes this biological mirror and bounces back toward the front of the eye. This reflection forces the light to pass through the photoreceptor layer a second time, effectively doubling the animal's opportunity to perceive a faint image. This clever recycling of light provides a significant evolutionary advantage for predators and prey alike in low-light conditions. Because the light is reflected back through the sensing cells, the animal can see shapes and movements that would be completely invisible to a human eye. This efficiency is what allows a forest owl or a wandering fox to move through a moonless woods with total confidence. The physical makeup of this layer varies between species. sometimes consisting of organized crystals of guanine or specialized protein fibers. Regardless of its specific chemical composition, its primary function remains the same: to act as a high-efficiency retroreflector that maximizes the utility of every stray photon. When you see a cat's eyes glowing with an eerie, metallic intensity in the beam of a flashlight, you are witnessing this physics in action. This phenomenon, often called Ishing, is the visible evidence of the tapetum lucidum doing its job of reflecting light back out of the eye. The glow is not produced by the animal itself, but is instead the redirected light of your own light source being bounced back toward you. Because the reflective layer is curved and positioned behind the lens, it tends to focus the reflected light into a tight beam, making the eyes appear to burn with an internal fire. The specific color of the glow can vary from green to gold or even blue, depending on the minerals and structures present in that specific animal's eye. It is a striking example of how the laws of optics are utilized by evolution to solve the problem of darkness. While we rely on artificial lights to navigate the night, these animals carry a piece of optical technology within their own bodies. This biological mirror ensures that the world never truly goes dark for them, as they can stitch together a visual map from the smallest fragments of starlight. The tapetum lucidum represents a perfect intersection of biology and physics, where a simple reflection becomes a tool for survival. As we consider these relaxing facts, it becomes clear that mirrors are not just objects we hang on our walls, but are fundamental components of the living world. The silent glow of a predator's eyes in the dark is a reminder of the quiet, efficient way that light behaves when it meets a surface designed to catch it. While light reveals the world through electromagnetic radiation, the world of sound operates through the physical movement of matter itself. These mechanical compression waves travel by bumping molecules into one another in a rhythmic sequence. When these waves hit a solid barrier, they do not simply vanish into the material. Instead, they bounce back into the open air in a process known as acoustic reflection. This physical behavior is the foundation for every sound we hear in an enclosed space, from the subtle resonance of a small room to the vast, lingering tones of a cathedral. Just as a mirror redirects a beam of light at a specific angle, a hard surface redirects a sound wave. The angle at which the sound hits the wall is the same angle at which it reflects away. This predictable geometry allows architects to shape the way we experience music and speech. In a well-designed concert hall, the walls are angled to guide these reflections toward the audience, ensuring that the sound remains clear and immersive. This is science for sleep, where the predictable laws of physics create a sense of order in our environment. Have you ever wondered why sound waves mimic light waves so closely despite being made of entirely different physical components? When a sound reflection returns to the listener with enough delay, It creates the phenomenon we know as an echo. For the human brain to perceive a distinct echo rather than just a thickening of the original sound, there must be a specific interval of time between the two events. Generally, the human ear requires a delay of at least 1/10 of a second to distinguish a reflected sound as a separate entity. Because sound travels at approximately 343 meters per second in room temperature air, this delay occurs when the reflecting surface is at least 17 meters away. If the surface is closer than this distance, the reflection arrives too quickly for the brain to separate it from the source. Instead of an echo, we hear what is called reverberation, which is the lingering quality that gives a voice richness or depth. This is why singing in a tiled bathroom sounds more resonant than singing in a carpeted bedroom. The hard tiles reflect the sound waves multiple times within a few milliseconds, blending them into a single, continuous auditory texture. The physics of reflection becomes even more fascinating when the surface is not flat, but curved. In certain architectural structures known as whispering galleries, a circular or elliptical wall can catch sound and guide it along its perimeter. Because the sound waves hit the curved surface at a very shallow angle, they skip along the wall like a stone skipping across the surface of a pond. This allows a person standing on one side of a massive dome to hear a whisper from someone on the opposite side with startling clarity. St. Paul's Cathedral in London and Grand Central Terminal in New York are famous examples of this acoustic perfection. In these spaces, the curve of the masonry acts as a specialized mirror for pressure waves. The sound does not dissipate into the center of the room, but remains hugged against the wall, preserved by the geometry of the architecture. It is a reminder that the laws of reflection apply to the invisible vibrations of the air, just as surely as they apply to the brightest beam of light. These relaxing facts show us that even the air around us is shaped by the silent, steady rules of symmetry and bounce. Deep within the fundamental architecture of our reality, there exists a principle far more profound than the simple reflection of a face in a glass pane. This is the concept of symmetry, a term that in physics describes a situation where a system remains unchanged even after a specific transformation is applied to it. If you rotate a perfect circle, for example, its appearance does not change, meaning it possesses rotational symmetry. This idea of staying the same through change is not just an aesthetic quality, but the very anchor that holds the laws of the universe in place. In the year 1915, a brilliant mathematician named Emmy Noether changed the course of science forever by uncovering a hidden bridge between these symmetries and the physical world. Her work, which is now famously known as Noether's theorem, proved that every continuous symmetry in nature is directly linked to a specific conservation law. Before this discovery, scientists knew that things like energy and momentum were conserved, but they didn't truly understand why. Noether showed that these balances exist because the universe itself is a kind of mathematical mirror, reflecting its own consistency across time and space. To understand continuous symmetry in the most accessible way, imagine a smooth, infinite plane stretching out in every direction. If you were to slide a small object across this plane by exactly 1 meter, the physics of that object would not change because the environment is uniform. This is called translational symmetry, and it is the reason why the law of gravity works the same way in your bedroom as it does on the surface of a distant moon. Because the universe does not change its fundamental rules based on where you are located, the physical quantity we call momentum must be conserved. This relationship between a symmetry and a law is one of the most elegant facts in all of human knowledge. It suggests that the stability of our world is not an accident, but a result of a deep, underlying perfection. Just as a mirror creates a perfect correspondence between an object and its image, the universe maintains a perfect correspondence between its geometric properties and its physical behavior. When we observe a planet orbiting a star or a child playing with a ball, we are seeing Noether's theorem in constant, silent action. How is it possible that a purely mathematical idea can dictate the physical movement of every atom in existence? This question leads us into the heart of theoretical physics, where the distinction between a shape and a law begins to blur. In this realm, symmetry acts as a silent guardian of order, ensuring that the energy within a closed system can never simply vanish into nothingness. It is as if the universe has a memory of its own balance, a mathematical mirror that prevents any part of the cosmic equation from falling out of alignment. The perfection of a mathematical mirror is perhaps the only thing more precise than the highest quality glass we can manufacture. While a glass mirror might have tiny imperfections or absorb a small fraction of light, the symmetries described by Emmy Noether are absolute and unwavering. They provide the quiet, steady foundation upon which all of science for sleep is built, allowing us to trust that the sun will rise and the stars will follow their predicted paths. This sense of cosmic consistency is a deeply comforting thought, suggesting a universe that is fundamentally orderly and predictable. Spatial translation symmetry is the fundamental idea that the laws of nature are identical regardless of your location. If you conduct a physics experiment in a quiet forest and then move the entire setup to a different city, the results will remain exactly the same. This uniformity means that no single point in space is more special or has different physical properties than any other point in the entire universe. This specific symmetry of space is the physical reason why linear momentum is always conserved. Because the fabric of space is smooth and identical from 1 millimeter to the next, an object's state of motion cannot simply change without a clear external cause. When two objects collide, They trade their momentum like a perfectly balanced currency because the underlying rules of the vacuum are the same for both participants. Scientists often use the term homogeneity to describe this seamless quality of the cosmic background. If space were lumpy, or if its nature changed every few miles, you would feel sudden jolts of acceleration or deceleration as you moved through the different regions. Instead, we experience a graceful and predictable glide through the void because the medium of space itself is perfectly consistent and unwavering. The universe also possesses a property known as rotational symmetry, which means that the direction you point an object does not change the physics acting upon it. Whether a laboratory is oriented toward the north or rotated 45 degrees to the west, every internal measurement and chemical reaction will proceed in an identical manner. This independence from orientation ensures that the geometry of the cosmos is not biased toward any particular heading or angle. Rotational symmetry is the mathematical parent of the conservation of angular momentum, a law that governs anything that turns or circles. This is why a spinning top stays upright for a surprising amount of time. Its motion is protected by the symmetry of the three-dimensional space it occupies. Only the external interference of friction or air resistance can eventually steal that momentum away and bring the object to a rest. On a much larger scale, this conservation of angular momentum is what keeps the moon in its steady, eternal orbit around our planet. Without this constant mathematical balance, the moon might drift erratically or change its speed without any external influence. The predictability of these massive celestial cycles is a cornerstone of science for sleep, offering a quiet assurance that the heavens move in a stable and orderly fashion. In the field of cosmology, the term isotropic is used to describe a universe that looks identical regardless of which way a telescope is pointed. When researchers look at the furthest reaches of the sky, the distribution of distant galaxies appears roughly the same in every direction. This observation suggests that the fundamental mirrors of space were established at the very beginning of time and have remained perfectly intact across billions of light years. These deep symmetries act as the silent guardians of the physical world, reflecting the same laws back to us no matter where we travel. They represent a level of mathematical perfection that human engineers can only hope to approximate in a laboratory setting. By understanding these invisible patterns, we gain a clearer picture of a universe that is built on a foundation of absolute and unwavering logical consistency. Even at the microscopic level of quantum mechanics, the conservation of momentum remains a non-negotiable rule of the physical world. When subatomic particles interact at incredible speeds, the total momentum before and after the event must be perfectly balanced. This allows scientists to calculate the properties of entirely new particles by observing the subtle recoil they leave behind on the objects we can actually see. Beyond the physical dimensions of space, there is a more elusive mirror that governs the flow of the universe. This concept is known as time reversal symmetry, or T-symmetry, and it suggests that the fundamental laws of physics do not actually distinguish between the past and the future. If a video of a physical process were recorded and then played in reverse, the laws of nature would still be perfectly satisfied. This symmetry implies that at the most basic level, time is a two-way street where every action has a mathematically valid counterpart, moving in the opposite temporal direction. Most of the primary equations that describe our physical world, such as those found in Newtonian mechanics, function with perfect precision, regardless of the direction of time. In these formulas, the variable representing time can be positive or negative without breaking the logic of the system. This means that according to the math, a planet orbiting a star could technically revolve in the opposite direction without violating any core principles of gravity or motion. The universe appears to be indifferent to the arrow of time when we look strictly at the rules of how objects move and interact. At the microscopic level, this symmetry becomes even more apparent when observing the behavior of individual atoms and molecules. When two gas particles collide and bounce away from each other, the interaction looks identical whether the sequence is viewed forward or backward. There is no inherent clue in the collision itself to tell an observer which event happened first and which happened second. This microscopic indistinguishability is a fundamental fact of the subatomic world, where the mirror of time remains clear and undistorted by the complexities of the larger world we inhabit. If a single electron moves through a magnetic field, its path is dictated by equations that are entirely reversible. A physicist watching a recording of this movement would find it impossible to determine if the film was being projected correctly or in reverse based solely on the particle's trajectory. This suggests that the building blocks of our reality are governed by a deep, temporal balance that does not favor one direction over another. It creates a vision of a universe where every moment is a reflection of its own potential to be undone. However, a contrasting scientific fact exists when we move from the world of single particles to the macroscopic world of everyday objects. While individual atoms follow reversible paths, large systems of trillions of atoms are governed by the second law of thermodynamics, which introduces the concept of entropy. Entropy is a measure of disorder, and in any closed system, it must always increase over time. This creates a one-way arrow that makes certain events, like a glass shattering or heat spreading through a room, appear impossible to reverse in our daily experience. This distinction between the reversible laws of physics and the irreversible flow of entropy is one of the great mysteries of modern science. While the microscopic mirror of time is perfect, the macroscopic world seems to lose that symmetry as complexity grows. In a quiet room, The gradual cooling of a cup of tea is a silent witness to this relentless forward march of energy. Even though the individual molecules are bouncing in a way that could technically be reversed, the collective whole moves steadily toward a state of equilibrium and rest. The concept of parity symmetry suggests that the laws of physics should remain unchanged if all three spatial coordinates were inverted through a central point. In simpler terms, this means the universe ought to behave identically to its own mirror image. For decades, physicists believed this was an absolute law of nature, assuming that the fundamental forces did not care about the difference between left and right. This symmetry, often called p-symmetry, implies that any physical process you observe in our world should be just as possible if it were reflected in a giant cosmic-looking glass. Imagine a world where every right-handed person was left-handed and every clock spun in the opposite direction. If parity symmetry were perfect, there would be no experiment you could perform to prove you were in a reflected reality rather than the original one. The orbits of planets, the falling of an apple, and the flow of electricity would all follow the same predictable rules. This deep sense of balance provided a comforting mathematical elegance to the early pioneers of quantum mechanics, who viewed the mirror as a perfect tool for understanding the structure of space itself. However, a groundbreaking scientific fact emerged in 1956 that forever changed our understanding of this spatial balance. Two theoretical physicists, Tsung-Dao Lee and Chen-Ning Yang, proposed that while parity might hold for most forces, it might be violated by the weak nuclear force. This force is responsible for certain types of radioactive decay, such as the process that powers the sun and allows unstable atoms to transform. They realized that no one had ever actually tested whether the weak force respected the mirror image rules that seemed so obvious in the rest of physical science. To test this unsettling idea, Dr. Qin-Xiang Wu conducted a definitive experiment at the National Bureau of Standards involving the radioactive decay of cobalt-60 atoms. By cooling the cobalt to temperatures near absolute zero and using a powerful magnetic field, she aligned the spinning nuclei of the atoms in a single direction. If parity were a true law of the universe, the electrons emitted during the decay should have been thrown out in equal numbers in all directions. There should have been no preference for up or down, or left or right, in the chaotic shedding of particles from the cooling metal. The results of the Wu experiment were published in the journal Physical Review in 1957, sending shockwaves through the scientific community. Dr. Wu discovered that the electrons were far more likely to be emitted in a direction opposite to the nuclear spin. This meant the weak nuclear force actually had a handedness, preferring one direction over another in a way that a mirror image would flip. This fact proved that the universe is not actually a perfect mirror of itself at the subatomic level. revealing a fundamental asymmetry built into the very fabric of matter. This discovery was so profound that it led to a Nobel Prize for Li and Yang just a year later, as it forced every physicist to rethink the nature of reality. It means that on a microscopic scale, the universe can distinguish between a left-handed system and a right-handed one. While the macroscopic world of bouncing balls and flowing rivers appears symmetrical, the silent world of nuclear decay possesses an inherent orientation. This strange, subtle bias suggests that space itself has a preferred geometry that we are only beginning to truly comprehend. The concept of symmetry in the universe extends far beyond the physical orientation of left and right, reaching into the very substance of matter itself. This leads to the scientific principle known as charge symmetry, or C-symmetry, which suggests that the laws of physics should remain identical if every particle were replaced by its oppositely charged counterpart. Deep within the framework of quantum field theory, every fundamental particle has a corresponding twin known as an antiparticle. Antimatter is not a science fiction concept, but a verified physical reality, consisting of particles that possess the exact same mass as ordinary matter while carrying an inverted electrical charge. The relationship between a particle and its antiparticle is often described by physicists as a form of cosmic reflection. An antiproton, for example, serves as a perfect mirror image of a standard proton. While they share identical gravitational properties and internal structures, the antiproton carries a negative charge, precisely mirroring the positive charge of the proton we find in the heart of every atom. Positrons represent another side of this reflective reality, acting as the antimatter version of the electron. In a positron, the mass remains unchanged from the light, dancing electron, yet its charge is positive rather than negative. This symmetry is so precise that if you could construct an entire person out of antimatter, they would look and behave exactly like a person made of matter, provided they remained isolated from our world. The most famous fact regarding this relationship involves the moment these two mirrored realities finally meet. When a particle of matter touches its corresponding antiparticle, they undergo a process known as annihilation. In this instantaneous event, the mass of both particles is converted entirely into pure energy, typically in the form of high-energy gamma-ray photons. This conversion is the most efficient process in the known universe for turning solid mass into light. Unlike nuclear fission or fusion, which only convert a small fraction of a percent of mass into energy, matter-antimatter annihilation follows Einstein's famous equation to its absolute limit, releasing every last drop of potential energy stored within the particles. The existence of antimatter was first predicted mathematically by Paul Dirac in 1928, a discovery that suggested the vacuum of space is far more complex than a simple void. Today, Researchers at facilities like CERN utilize massive magnetic traps to briefly suspend antiprotons, preventing them from touching the walls of their containers. Even a single touch would result in a flash of light as the mirror image particles vanish into the surrounding matter of the laboratory. The prevailing scientific consensus, supported by observations of the early universe, suggests that matter and antimatter were created in nearly equal amounts during the Big Bang. However, a tiny, unexplained asymmetry allowed a small amount of extra matter to survive the initial era of annihilation. We exist today only because the cosmic mirror was slightly imperfect, leaving behind the material world we see around us, while the vast majority of its reflection vanished into light. As we move into the early months of 2026, our understanding of the distant universe has been fundamentally reshaped by the most sophisticated mirrors ever launched into the silence of space. The James Webb Space Telescope has now completed 4 full years of science operations, delivering a continuous stream of data that has forced astronomers to rethink the formation of the earliest galaxies. At the heart of this technological triumph sits a primary mirror spanning over 6 meters across, acting as a massive light bucket to catch the oldest photons in existence. This iconic golden surface is actually composed of 18 hexagonal segments that work together as a single, seamless reflective unit. Engineers chose this honeycomb pattern because it allowed the massive structure to be folded inside a rocket fairing and then unfolded with nanometer precision once it reached its destination 1,000,000 miles from Earth. Each segment is a masterpiece of material science, designed to remain perfectly still while floating in the deep freeze of the Lagrange point. The substrate of these mirrors is not made of traditional glass, which would be far too heavy and prone to cracking under extreme thermal stress. Instead, each segment is crafted from beryllium, a rare metal known for being incredibly stiff yet surprisingly lightweight. Beryllium possesses a unique physical property called a low coefficient of thermal expansion, meaning it does not warp or change its shape as the temperature fluctuates. This stability is critical because the telescope operates at temperatures below 40 degrees Kelvin, which is colder than the surface of Pluto. If the mirrors were to shift by even a fraction of the width of a human hair, the resulting images would be hopelessly blurred and scientifically useless. NASA selected beryllium specifically because it maintains its exact curvature in these cryogenic conditions, ensuring the light from the first stars stays in sharp focus. While the mirrors are made of beryllium, their shimmering appearance comes from an incredibly thin outer coating of 24-karat gold. This gold layer is only about 700 atoms thick, which is so thin that a quantity of gold the size of a golf ball was enough to coat the entire 25 square meter surface. Gold was not chosen for its aesthetic beauty or its value, but for its unparalleled ability to reflect infrared light. Most of the light traveling from the edge of the observable universe has been stretched by the expansion of space, shifting it out of the visible spectrum and into the long wavelengths of the infrared. While a standard silver or aluminum mirror is excellent at reflecting the light our human eyes can see, gold is far superior at bouncing these longer infrared waves toward the telescope's sensors. By using this metallic coating, the telescope captures 98% of the infrared photons that hit its surface. Over the last 4 years, this reflective golden eye has peered through dense clouds of cosmic dust that were previously impenetrable to older observatories. It has captured the chemical signatures of water and carbon dioxide in the atmospheres of planets orbiting distant suns, turning reflections into a map of potential habitability. Every image we receive is a testament to the precision of these 18 beryllium plates and their microscopic gilding. The success of this mission has proven that we can create artificial mirrors capable of outperforming anything found in the natural world. By carefully selecting elements like beryllium and gold, scientists have extended the reach of human vision across billions of light years. We are now living in an era where the reflections captured in deep space provide a direct link to the very beginning of time itself. The pursuit of optical perfection has led engineers to experiment with materials that seem entirely counterintuitive for a precision instrument. While we usually think of a mirror as a rigid, unyielding slab of glass, some of the most powerful telescopes ever built use a reflective surface that is entirely liquid. These are known as liquid mirror telescopes, and they represent a strange but highly effective feat of modern engineering. Instead of grinding and polishing a solid material for months or years, these telescopes rely on the fundamental laws of fluid dynamics to create a flawless shape. The core of this technology is a large, shallow container filled with a thin layer of liquid mercury, a heavy metal that remains in a fluid state at room temperature. Mercury is an exceptional choice for this purpose because it is highly reflective, acting much like a silvered coating on a traditional mirror. However, a still pool of mercury is perfectly flat, which is not useful for focusing light from distant stars into a single point. To transform this flat surface into a functional tool for astronomy, the entire container must be set into a slow, perfectly steady rotation. As the vat of mercury begins to spin, a remarkable transformation occurs within the liquid. The rotation introduces centrifugal force, which pulls the liquid metal outward toward the edges of the container. At the same time, the force of gravity is pulling the mercury straight down toward the center of the Earth. When these two opposing forces, the outward push of rotation and the downward pull of gravity, reach a state of equilibrium, the surface of the liquid naturally settles into a mathematically perfect shape. This shape is known as a paraboloid, which is the exact geometric curvature required to reflect parallel rays of light into a single, sharp focal point. In a traditional glass mirror, achieving this parabolic curve requires incredibly precise mechanical grinding that must be accurate to within a fraction of a wavelength of light. With a liquid mirror, the physics of the rotating frame does all the work automatically. As long as the rotation speed remains constant, the liquid surface remains a flawless parabola, free from the microscopic scratches or imperfections that can plague solid surfaces. The Large Zenith Telescope in Canada was one of the most famous examples of this engineering marvel, utilizing a 6-meter-wide pool of spinning mercury. Because the mirror is a liquid, it must always remain level to maintain its shape, which means these telescopes can only look straight up at the zenith of the sky. While this limits where the telescope can point, it allows for an incredibly large and inexpensive collecting area for surveying the strip of space that passes directly overhead. The simplicity of this design also makes it incredibly cost-effective compared to solid glass mirrors of the same size. A liquid mirror can be constructed for a small fraction of the cost of a traditional one, as it requires no heavy casting or years of delicate polishing. This efficiency has led scientists to consider even more ambitious designs, such as placing liquid mirrors on the moon, where the low gravity and lack of atmosphere would allow for even greater precision. The physics of these spinning surfaces demonstrates how nature can sometimes provide the most elegant solutions to complex technical problems. By simply allowing gravity and rotation to find their own balance, we can create a reflective surface that is essentially self-healing and perfectly smooth. This interaction between movement and reflection is not limited to visible light, as the same principles govern how surfaces interact with invisible waves of energy. These liquid surfaces may one day even play a role in how we manage the reflection of intense heat in extreme environments. The interaction between light and solid surfaces takes a peculiar turn when we examine the technology used in security and observation. One-way glass is often perceived as a specialized material with a magical ability to be opaque on one side and transparent on the other. In reality, the physics of these surfaces relies on a delicate balance of light transmission and reflection, rather than any directional property of the glass itself. These surfaces are more accurately described as half-silvered mirrors because of the way they are manufactured. A standard mirror has a thick, opaque layer of metal applied to the back of the glass, which reflects almost all the light that hits it. A half-silvered mirror is different because the metallic layer is applied so thinly that it becomes sparse at the atomic level. This microscopic coating of aluminum or silver is distributed across the glass surface in a way that allows about half of the incoming light to bounce off. The other half of the light passes directly through the gaps in the metallic molecules. How is it possible for light to pass through a solid layer of metal in this way? The answer lies in the incredible thinness of the coating, which is often only a few dozen atoms thick. At this scale, The metal acts less like a solid wall and more like a very fine mesh screen. If you were to look at this coating under an electron microscope, you would see that it is not a continuous sheet, but a series of tiny, reflective islands. This allows the glass to maintain two distinct identities simultaneously by acting as both a window and a mirror. The famous interrogation room effect is entirely an optical illusion created by an extreme difference in lighting between two rooms. For the illusion to work, one room must be brilliantly illuminated, while the observation room remains almost entirely dark. A person in the bright room sees a reflection of themselves because the light hitting the glass from their side is so intense. Even though half of that light is passing through to the other side, the half that reflects back is much brighter than anything coming from the dark room. Someone sitting in the darkened observation room experiences the opposite effect. Because their room is dark, there is very little light to reflect off the glass and back into their eyes. Instead, they see the 50% of light that is transmitting through the glass from the brightly lit side. This transmitted light is much stronger than their own dim reflection, making the glass appear like a clear window into the next room. If the lights were turned up in the observation room and dimmed in the interrogation room, the effect would instantly reverse. The person who was previously hidden would suddenly see their own reflection, while the person on the other side would be able to see through. This proves that the glass is not one way in a physical sense. It treats light traveling in both directions exactly the same way. The phenomenon is a result of how our eyes and brains prioritize the brightest source of information in our field of view. Science for sleep often reveals that the most complex-seeming illusions are actually the result of simple, elegant physics. This specific type of glass is used extensively in high-end architecture and scientific instruments, where light needs to be split into two paths. By carefully controlling the thickness of the metallic vapor during the manufacturing process, engineers can choose the exact ratio of reflection to transmission. This precision ensures that the half-silvered surface performs its quiet duty, balancing the flow of photons between two worlds. Beneath the familiar world of mirrors and silvered glass lies a realm governed by the quiet, counterintuitive laws of quantum mechanics. In this microscopic landscape, the very idea of a solid surface begins to dissolve into something much more fluid and mysterious. One of the most breathtaking phenomena in this field is known as quantum reflection, a process where matter behaves in ways that defy our everyday experiences with physical contact. It is a world where atoms can bounce off a solid object without ever truly touching its surface, redirected by forces that act across a tiny, invisible gap. At the heart of this discovery is the understanding that every particle of matter also possesses the properties of a wave. When atoms are cooled to temperatures just a fraction of a degree above absolute zero, their movements slow down to a meditative crawl. In this state, Their wave-like nature becomes their most dominant characteristic, stretching out and becoming more pronounced. As these slow-moving, ultra-cold atoms approach a solid surface, they do not behave like tiny billiard balls hitting a wall, but rather like ripples on a pond approaching a hidden reef. The surface of any solid material exerts a subtle pull on nearby atoms known as the Casimir-Polder force, which is a specific type of electromagnetic attraction. In our macroscopic world, we expect an object being pulled toward a surface to simply accelerate until it makes physical impact. However, at the quantum level, if an atom is moving slowly enough, the sudden change in this attractive potential acts like a sharp cliff edge. Instead of falling into the surface and sticking to it, the atom's wave function experiences a sudden disruption that causes it to turn around and head back the way it came. This happens because the wave nature of the atom cannot adjust quickly enough to the intensity of the pull as it nears the solid boundary. The transition is so abrupt that the atom is essentially reflected by the vacuum itself just before it reaches the actual material. It is a moment of pure, silent redirection, occurring in a space so small it is almost impossible to visualize. This process allows scientists to manipulate matter with incredible precision, using the vacuum near a surface as a perfectly smooth, frictionless mirror for atoms. How can a force that is meant to pull things together actually result in pushing them away? The answer lies in the delicate balance of wave mechanics, where the shape of the potential energy determines the path of the particle. If the attraction becomes too strong too quickly, the wave is reflected by the very intensity of that change. It is a beautiful irony of physics that an attractive force, when encountered with enough stillness and patience, can act as a flawless shield. This phenomenon has been verified in laboratories using surfaces made of silicon or even liquid helium, which provide a stable backdrop for these fragile interactions. Research published in journals like Physical Review Letters details how these ultra-cold atoms can be guided along reflective paths without ever losing their quantum coherence. Because they never touch the surface, they never transfer heat or energy to it, allowing them to remain in their pristine, chilled state. This makes quantum reflection an essential tool for the future of quantum computing and high-precision sensing. Relaxing facts about the subatomic world remind us that the closer we look, the less solid the universe actually becomes. Even the most rigid diamond or piece of steel is mostly empty space, held together by fields of energy that hum with a quiet, invisible logic. When we see an atom bounce off nothingness, we are witnessing the fundamental grain of reality showing us its true face. It is a face of symmetry, waves, and silent transitions that occur far below the threshold of human sight. In the stillness of a laboratory, this process happens millions of times, a rhythmic dance of particles and waves that never makes a sound. There is no friction, no impact, and no wear on the materials involved. It is a form of reflection that is perfectly clean and perfectly efficient, governed by the mathematical beauty of the Schrödinger equation. As we contemplate these tiny, distant bounces, we can begin to see the entire universe as a collection of waves reflecting and interfering in a vast, silent ocean of potential. The vacuum of space is not truly empty, but rather a sea of fluctuating energy that exists even at temperatures of absolute zero. When two uncharged, perfectly conducting mirrors are placed just a few micrometers apart in this void, they begin to interact with these invisible fluctuations in a way that defies our everyday intuition about solid objects. Because the plates are so close together, they restrict the types of energy waves that can exist in the narrow gap between them. The Casimir effect is the name given to the physical force that arises from this restriction of quantum vacuum fluctuations. In the vastness of open space, virtual particles and their associated waves can take on any possible wavelength, creating a balanced pressure from all directions. However, the two parallel mirrors act as a boundary that only allows certain specific wavelengths to fit inside the small gap, much like the way a guitar string can only vibrate at certain frequencies based on its length. By excluding the longer wavelengths from the space between the plates, a difference in energy density is created between the inside and the outside of the mirror system. There are more possible wave states pushing from the outside than there are pushing from the inside. This imbalance results in a measurable physical force that draws the two mirrors toward each other, effectively pushing them together using the energy of empty space itself. This phenomenon was first predicted by Dutch physicist Hendrik Casimir in 1948, but the forces involved are so incredibly small that they remained difficult to prove for many decades. It wasn't until the late 1990s that experimental techniques became precise enough to confirm his theory with high accuracy. Scientists used sophisticated torsional pendulums and electromechanical systems to detect the tiny movements caused by these vacuum pressures. Research published in the journal Science has detailed how these measurements have reached a level of precision where the Casimir force can be mapped across different materials and temperatures. These experiments have shown that the force is not just a theoretical curiosity, but a real, tangible pressure that must be accounted for in the design of microscopic machines. At the scale of nanotechnology, these sticky, vacuum forces can cause tiny components to clump together, presenting a unique challenge for engineers building the smallest devices in the world. Have you ever wondered if the voids of the universe are actually heavy, with the weight of unseen possibilities? The discovery of the Casimir effect changed our fundamental understanding of what a vacuum is, shifting it from a concept of nothingness to a dynamic field of activity. It suggests that even in a total dark silence, There is a structural pressure to reality that can move physical objects. This force reminds us that the boundaries of a mirror do more than just reflect light. They define the limits of the quantum waves that can exist within their reach. In some specialized experiments, researchers have even explored the possibility of a repulsive Casimir force by using different materials or fluids between the plates. This would theoretically allow for quantum levitation, where the mirrors are held apart by the vacuum itself without any physical support. Such concepts continue to push the boundaries of physics, showing how the simple act of placing two reflections near one another can reveal the hidden machinery of the cosmos. As we look at the quiet, still surfaces of these microscopic mirrors, we are looking at the frontier of human knowledge. The force that nudges them together is a whisper from the quantum world, a reminder that the vacuum is alive with energy. Science for sleep allows us to appreciate these deep complexities of the physical world while remaining anchored in the calm, steady logic of observation and measurement. Beyond the microscopic boundaries of quantum forces, the physics of reflection and distortion extends into the silent reaches of deep space. We often think of mirrors as solid objects crafted by human hands, yet the universe possesses its own way of redirecting the path of light through the sheer influence of gravity. According to the principles of general relativity, space is not a rigid, empty void, but a flexible fabric that can be curved and warped by the presence of massive objects. When a beam of light travels through this curved space, it does not follow a straight line in the traditional sense, but instead traces the contours of the gravitational well it encounters. This phenomenon is known as gravitational lensing, and it effectively turns the most massive structures in the cosmos into natural, albeit distorted, lenses and mirrors. When a colossal cluster of galaxies sits directly between an observer on Earth and a much more distant light source, the cluster's immense gravity pulls on the passing photons. As these light particles are tugged inward, their trajectory is bent around the central mass, much like light passing through the curved glass of a magnifying lens. This process can magnify the distant object, allowing astronomers to see galaxies that would otherwise be far too faint and remote to detect with even our most advanced technology. The visual results of this cosmic bending are often as beautiful as they are strange, appearing as glowing arcs or concentric circles in the dark. In some rare and perfect alignments, the gravity of the foreground cluster is so precisely positioned that it splits the light from the background galaxy into multiple identical copies. An observer looking through a telescope might see 4 distinct images of the exact same quasar, arranged in a cross-like pattern around a central mass. This creates a functional mirror effect, where the same event in deep time is reflected back to us from several different angles simultaneously. These duplicated images are not merely visual tricks, but are reliable records of the same light rays taking slightly different paths through the warped geometry of space. Because each path may have a different length, the light in one, reflected, image might arrive at our sensors weeks or months after the light in another. This allows scientists to watch a supernova explode in one part of the sky and then wait for the same explosion to be replayed in another mirrored image. By using its own mass to bend and reflect its history, the universe provides a way for us to witness the same moment of ancient light multiple times. Science for sleep reminds us that even the largest scales of the cosmos follow these elegant, predictable rules of geometry and light. The way a surface interacts with the warmth of the sun is fundamentally different from how it reflects the light we see with our eyes. While a white shirt might look bright and reflective, it often absorbs a significant amount of the invisible infrared radiation that carries thermal energy. To truly manage the flow of heat, we must look at the electromagnetic spectrum beyond the narrow band of visible colors. This is where the physics of thermal reflection becomes a vital tool for survival in extreme environments. Metals possess a unique atomic structure that makes them exceptionally talented at bouncing back long-wave infrared radiation. In a conductive metal like aluminum or gold, the electrons are relatively free to move in response to an incoming electromagnetic wave. When a wave of radiant heat strikes a metallic surface, these mobile electrons oscillate rapidly, creating a counterfield that rejects the incoming energy. This process allows a thin layer of metal to reflect up to 97% of radiant heat, even if the layer is only a few atoms thick. This specialized branch of physics is the foundation for the thin, crinkly sheets known as emergency thermal blankets or mylar. These blankets are typically made by vapor depositing a microscopic layer of aluminum onto a flexible plastic substrate. When wrapped around a person, the metallic side faces inward to reflect the body's own radiant heat back toward the skin. Because the heat is reflected rather than absorbed or conducted away, the person stays warm using nothing but their own biological energy. Radiant heat travels through the vacuum of space just as easily as light, making thermal management a matter of life and death for satellites. Without the protection of reflective foils, the side of a spacecraft facing the sun would reach temperatures high enough to melt sensitive electronics. Engineers solve this by wrapping delicate instruments in multi-layer insulation, which looks like shimmering gold or silver gift wrap. These layers are separated by thin spacers to ensure that heat cannot skip from one sheet to the next through direct contact. Imagine a small probe orbiting a distant planet, positioned so that one side is baked by raw solar radiation, while the other faces the absolute cold of deep space. Inside the probe, the temperature must remain stable to keep its internal computers functioning within a narrow range. The outer reflective foil acts as a thermal mirror, bouncing the sun's intense infrared light back into the void before it can penetrate the hull. This simple application of infrared physics allows human-made machines to endure the harshest thermal gradients in the known solar system. The efficiency of these metallic mirrors is so high that even a single sheet can block a massive amount of energy from entering a system. In a quiet laboratory setting, a sensitive thermal camera can see the reflection of a person's heat in a sheet of aluminum just as clearly as a glass mirror shows a visual face. This invisible world of bouncing heat waves is constantly at work around us, even when we cannot see the radiation being redirected. Relaxing facts about the behavior of energy remind us that mirrors are not just for our eyes. They are the shields that guard the delicate balance of temperature in our world. The Earth itself functions as a massive, multifaceted mirror spinning through the dark velvet of space. This planetary reflectivity is known to scientists as albedo, a term derived from the Latin word for whiteness. It describes the fraction of solar energy that is reflected back into the vacuum rather than being absorbed by the ground or the oceans. On a global scale, this reflection is the primary mechanism that prevents our world from overheating under the constant gaze of the sun. Freshly fallen snow is perhaps the most efficient natural mirror on the surface of our planet. When sunlight strikes a field of pure, white snow, nearly 90% of that energy is immediately bounced back toward the sky. This high albedo ensures that the ground beneath the snow stays insulated and cool, even on a bright and sunny afternoon. In the quiet expanse of the Arctic, this reflective power acts as a continental shield, turning away vast amounts of solar radiation that would otherwise warm the Earth. Sea ice serves a similar and equally vital role in the delicate thermal balance of the high latitudes. While the deep blue water of the ocean absorbs the vast majority of the sunlight that hits it, the white cap of sea ice reflects that same light away. This contrast creates a powerful cooling effect that influences weather patterns and ocean currents across the entire globe. According to data from the National Oceanic and Atmospheric Administration, this reflective white surface is a cornerstone of the global climate system. How does the planet manage to mirror the sun so effectively while supporting such a diverse range of life? The answer lies in the constant interplay between the dark forests, the blue seas, and the brilliant white clouds that drift through the atmosphere. Each of these surfaces contributes to a collective albedo that keeps the average temperature of the Earth within a narrow, life-sustaining range. Clouds alone are responsible for a significant portion of this reflection, acting like soft, white blankets that bounce sunlight away before it ever reaches the soil. The Intergovernmental Panel on Climate Change has highlighted how even small shifts in this global reflectivity can lead to significant changes in surface temperatures. When ice melts and reveals the darker water or land beneath it, the albedo of that region drops sharply. Instead of reflecting the sun's energy like a mirror, the darker surface begins to absorb it, leading to a localized increase in warmth. This transition from a reflective state to an absorptive state is one of the most closely studied feedback loops in modern climate science. In a quiet, snow-covered forest, the silence is a testament to the stillness of this energy exchange. The light that filters through the trees is bright, but carries very little heat because the white surface beneath the branches is busy redirecting the sun's power. Science for sleep often finds its most peaceful examples in these vast, white landscapes where the laws of physics work silently to maintain the world's cool. Every snowflake acts as a tiny, hexagonal mirror, contributing its small part to the grand reflection of the planet. Even the deserts play a role in this reflective dance, with pale sands bouncing more light back into space than dark volcanic soil or dense tropical jungles. This patchwork of different reflective intensities creates a complex map of energy that satellites monitor from orbit every single day. By measuring the light that returns from the Earth, scientists can calculate exactly how much energy is being retained and how much is being sent back into the stars. This constant mirroring is a silent guardian, a physical property of our world that allows life to flourish in the gentle warmth of a balanced atmosphere. The transition from the physical world of light into the internal world of the mind reveals a different kind of reflection. Neuroscience explores how the brain interprets the images seen in a mirror, transforming a simple bounce of photons into a complex realization of the self. This process is not instantaneous at birth, but develops through specific stages of neurological maturation. In humans, the ability to recognize one's own reflection typically emerges between the ages of 18 and 24 months, marking a significant milestone in cognitive development, according to established developmental psychology. Before this developmental window opens, a young child might perceive the figure in the glass as a separate individual or a playmate. This cognitive shift requires the brain to integrate visual information with internal proprioception, which is the sense of where one's body is in space. When the brain successfully matches the movement it feels with the movement it sees in the reflection, it creates a unified map of the self. This internal alignment is a fundamental requirement for passing the mirror self-recognition test, a standard experimental procedure used to gauge self-awareness across various species. The mirror self-recognition test, often called the mark test, involves placing a small, odorless dye or sticker on an animal in a place they cannot see without a reflection. If the animal looks into a mirror and attempts to touch or remove the mark on their own body rather than touching the mirror itself, researchers conclude they possess a level of self-concept. Beyond humans, Only a few species have consistently passed this test, including great apes like chimpanzees and orangutans, as well as bottlenose dolphins and Eurasian magpies. These findings suggest that the neurological hardware required to process a reflection as self is rare in the animal kingdom. Within the architecture of the primate brain, a specific class of cells known as mirror neurons provides a biological basis for understanding the actions of others. First discovered in the ventral premotor cortex of macaque monkeys, these neurons exhibit a fascinating dual property that bridges the gap between doing and seeing. A mirror neuron fires both when an individual performs a specific physical action and when that same individual observes another performing a similar movement. This synchronized firing creates a neural representation of the action that is independent of who is actually moving. When you watch a reflection of your own hand gripping a glass, these neurons are highly active, reinforcing the connection between the intent of the motor command and the visual feedback of the result. This system allows the brain to simulate the movements of others within its own motor circuits, providing a fast and efficient way to learn through observation. Some researchers in the field of scientific psychology suggest that this system is what allows us to predict the goals and intentions of those around us by reflecting their physical states onto our own neural pathways. The localization of these neurons in the human brain includes the inferior frontal gyrus and the inferior parietal lobe, areas deeply involved in planning and executing complex tasks. In these regions, the brain does not distinguish between a direct view of an arm moving and a mirrored view of that same arm. The electrochemical response remains remarkably consistent. This neurological mirroring acts as a bridge between the sensory input of the eyes and the motor output of the muscles. Relaxing facts about our biology often point to this seamless integration, showing how the brain uses reflections to refine its own internal model of the world. Studies published in journals like Science and Nature have detailed how these neural circuits respond to different types of visual feedback. If a reflection is distorted or delayed, the mirror neuron system may struggle to synchronize, leading to a sense of cognitive dissonance. This occurs because the brain is constantly comparing the expected visual outcome of an action with the actual visual data it receives from the environment. When the two match perfectly, the brain confirms that the reflection is an accurate representation of reality. The complexity of this system highlights the immense processing power required to simply look in a mirror and understand what is being shown. It is a testament to the sophistication of the mammalian brain that it can take a two-dimensional plane of light and interpret it as a three-dimensional being with agency. As the brain processes these reflections, it maintains a quiet, constant dialogue between the eyes and the motor cortex, ensuring that our perception of ourselves remains stable and coherent throughout our lives. This internal mirroring is as much a part of our survival as the physical laws that allow the light to bounce off the glass in the first place. The material we often perceive as a permanent fixture of our homes possesses a hidden, incredibly slow life cycle that spans geological epochs. Many people believe a common myth that old cathedral windows are thicker at the bottom because the glass has flowed downward like a viscous liquid over the centuries. Scientific analysis of medieval glass confirms that these variations are actually the result of early manufacturing techniques, where hand-blown glass discs were naturally uneven, and builders simply placed the thicker edges at the bottom for stability. Glass is technically defined by physicists as an amorphous solid, a state of matter where the atoms are locked into a disordered, random arrangement rather than a neat crystal lattice. The internal structure of a mirror is far more rigid than its liquid-like appearance might suggest to the naked eye. At room temperature, the rate at which the molecules in silica glass could potentially rearrange themselves is so slow that it would take billions of years to observe even a microscopic change. This stability means that the mirrors created today are likely to remain functionally identical for as long as the environment around them stays controlled and dry. In an inert vacuum, free from the erosive forces of wind or chemical moisture, a high-quality glass mirror could potentially maintain its structural integrity for a duration exceeding the current age of the solar system. The atomic bonds within the glass are remarkably resilient, holding their positions with a quiet, stubborn persistence through the passage of deep time. While the silver or aluminum coating on the back of the mirror might eventually oxidize or flake away if exposed to the atmosphere, the glass substrate itself remains a silent witness to history. It does not evaporate, and it does not melt under normal terrestrial conditions, acting instead as a frozen snapshot of the moment it was cooled from a molten state. The science of materials shows us that the transition from a liquid to this amorphous solid state creates a substance that is uniquely suited for longevity. Consider the profound stillness of a mirror left in a subterranean vault, shielded from the sun and the changing seasons. As the millennia pass, the photons that occasionally strike its surface continue to bounce off with the same precision they did on the day the mirror was first polished. There is a certain peace in realizing that the physical laws governing reflection do not fatigue or wear out over time. The geometry of the bounce remains perfect, governed by the same electromagnetic principles that have existed since the early universe began to cool and become transparent. This endurance into the far future allows us to think of mirrors not just as household objects, but as potential time capsules for light. If a mirror were placed far enough away in space, it would reflect the image of our planet back to us across a bridge of many light years. This reflection would carry the visual history of our world, preserved in a stream of photons traveling through the void. In this way, the physics of reflection provides a silent, enduring record of existence that persists long after the original source of the light has changed or faded. The concept of deep time reminds us that the materials we interact with every day are part of a much larger, slower story of atomic stability. Every mirror you encounter is a testament to the incredible durability of silicon and oxygen atoms when they are fused together in a specific, glassy embrace. As we move toward the final thoughts of our exploration, we can appreciate the silent, unchanging nature of these reflective surfaces as they wait in the darkness. They do not demand our attention, yet they stand ready to return every ray of light that finds them, acting as a bridge between the present moment and the vast reaches of the future. The journey of a single photon begins in the heart of a star or the filament of a lamp, traveling through the vastness of space until it encounters a surface. This tiny packet of energy follows the most precise laws of the universe, bouncing with a mathematical grace that has remained unchanged since the beginning of time. Whether that reflection occurs on the surface of a mountain lake or the gold-coated mirrors of a telescope drifting 1,000,000 miles from Earth, the physics remains the same. We have seen how light interacts with the silvered backing of a household glass, creating a virtual world that mirrors our own with startling accuracy. This simple act of reflection is actually a complex dance of electromagnetism and atomic transitions occurring at speeds we can barely conceptualize. Beyond the glass and the silver, the very structure of our reality seems to be built upon these same principles of balance and symmetry. From the way subatomic particles interact to the massive gravitational lenses that warp the light of distant galaxies, the universe acts as its own mirror. We find comfort in the fact that the laws of physics do not change depending on where we stand or which direction we face. This fundamental consistency allows us to predict the movement of planets and the behavior of light with incredible certainty. Every reflection we see is a small, everyday reminder of the deep architectural harmony that governs everything from the smallest atom to the largest supercluster of galaxies. This symmetry extends into the hidden dimensions of the cosmos, where antimatter and matter exist as reflections of one another. We have explored how the concept of parity and charge allows us to understand the fundamental building blocks of existence. Even the flow of time itself carries a theoretical symmetry that challenges our everyday perception of the world. By looking into a mirror, we are not just seeing our own faces, but we are witnessing the manifestation of universal constants that have been fine-tuned over billions of years. It is a quiet, profound realization that the same light reaching your eyes tonight has been governed by these identical rules since the first stars began to shine. The study of these phenomena allows us to appreciate the intricate details of the natural world, From the reflective layer in a cat's eye to the shimmering heat of a desert mirage. Each fact we learn is like a polished surface, helping us see the world with greater clarity and a deeper sense of wonder. Science provides the tools to look beneath the surface of things, revealing a reality that is far more interconnected than it first appears. As we settle into the stillness of the present moment, the weight of this knowledge brings a sense of peaceful resolution. There is a vast, silent beauty in the way the universe explains itself through the simple path of a light wave. If you have enjoyed this peaceful exploration of the scientific world, please consider subscribing to join us for more quiet journeys into the wonders of our universe. The story of light and symmetry is one that never truly ends, as every photon continues its journey through the dark, waiting for the next surface to catch its glow. Learning about the world is a way of reflecting its beauty back into our own minds, creating a map of understanding that grows more detailed with every new discovery. In the silence of the night, the laws of physics continue their work without pause, maintaining the perfect order of the stars and the gentle bounce of light in the shadows. As the world grows quiet, we can rest in the knowledge that the universe remains a place of logic, symmetry, and enduring light. The quiet universe reflects its ancient light through the darkness, forever constant and perfectly still.